Okay, so this week in lab, we are kind of departing from the standard stuff that we've been doing. From the beginning of the semester, it's either been gravity, forces, momentum, velocity, stuff like that. Really standard classical mechanics, and I suppose waves can be grouped into classical mechanics as well, but I always viewed them as a separate and much more conceptually difficult topic. And historically, the study of waves and wave theory led to electricity and magnetism, like Maxwell in the 1800s, as well as quantum mechanics, like the as unclassical as you can be in the 1910s to 1940s with quantum mechanics. And so I wanted to review some practical matters with the setup, as well as some of the theory behind waves, because opening up this week's lab manual is a little bit more daunting than in previous weeks, where we were determining gravity in just another way. So let me share my screen, and we'll start talking about this stuff. Okay. Okay, so the setup that we're doing is taking a stretchy string and we are tying it to a post. This post here has a motor attached to it, and that motor will go through, the string will go through a peg attached to the motor. The motor will vibrate, and as such, it will send kind of shock waves down the string. It's kind of like if you take a hose when you're a kid and you like do the like the I don't know, whatever that the thing is, and you make kind of a wave, and it shoots down the edge of the thing, and the reason why this happens is explained incredibly well in a YouTube video by Khan Academy. They have, in particular, from the 1 minute to a 7 minute mark. And don't worry about these texts. I'll post that in the announcement as well. But they have a very good explanation of two fixed endpoint string, and why things like these antinodes and nodes form, and it has to do with this idea called superposition, which is, as I mentioned, why this led to the quantum mechanical things. It's the superposition principle of quantum mechanics, or of just wave mechanics. And so some of the simplifications that we're going to be doing in this lab, because of Corona times, we're not going to be weighing the string as it mentions in the lab manual. So the idea was that we want to use this equation to find the velocity of the wave. We're going to say what's the tension in the string, which is supplied by this hanging mass over here, and we're going to divide by the mass density, which would be the mass of the string, which in previous years we actually weighed it, divided by the length of the string. And so in this year, we're not going to do that. If you notice up here, it's already given to you. And so correspondingly, some of the things that you're going to cross out on your Google Sheet, no more weighing the string. The mass hanging off the thing is given to you. It's 150 grams. Yes, 150 grams. Getting the tension. This, if you would like, can actually be, because now so in previous years, what we were to do is take the length of the string being excited, taking the loose string, and adding them up into a quantity called L dash. And the idea was to take the mass density would be the mass of the string over L dash, but we're not doing that this year, so ignore that part. And so if you'd like, which is what I'll do right now, I'm going to take these cells and put them down here because they are really only used in part 2 anyway. So I'm just going to take that, and I block these off in red just to mention that you don't actually need to measure that anymore. These are given, as opposed to it used to be we would calculate it with those 3 cells as well as this cell. And so now we're just basically plugging into this formula. Now the next part I want to mention, you might be able to get it immediately because it's similar to something we've been doing, but the uncertainty for that is a little different. So as opposed to just an A over B quantity, propagating the uncertainty from, you have an uncertainty of A and an uncertainty of B. Now we've not only got exponents, but they're different powers of exponents that we have. And so the first step, this is still a fraction, so you're still going to be using equation 10 from that error PDF that we've been using. However, you are also going to use equation 11, which tells you that if you have an uncertainty in A, you can propagate it to a power of A with the power down here, taking one off the power, right? Normally we do the period squared or the length squared, and so it's normally a 1 here, but now it's going to be a negative 1/2 minus 1, and so writing it back in terms of square roots, it looks like that. So I just want to alert you of that. Okay, so now on to part 2, where we are going to be using the length here, and what we're going to be doing is looking at, so part 1 is you don't turn the motor on really at all. Part 2, you do turn the motor on and you start observing these harmonics. Harmonics are what they're called, when things constructively interfere. That's what is explained in the Khan Academy video. And so you're going to be observing some of these, and then you are going to be finding the frequency at which that happens. And so the frequency is not, we're not going to be measuring, how fast that happens on the wave. What we're going to be doing is measuring how fast the motor is driving the string. And so a picture to explain that here, I mean, you'll see it when you get to lab, but what's going on here is that there's a cylinder that's rotating due to this little engine that's pushing things. It is attached to a kind of this rigid thing that is on a hole here and through the string, and as that goes up and down, it shakes the string up and down. And so a way that we devised to measure the frequency of how fast this goes is to measure the period, because we know that the frequency is 1 over the period. And so what we're going to do is time how long it takes for this engine to rotate the cylinder. And so we stuck a little flag to it. And as it goes around, it blocks and unblocks the photo gate. And so we get a time for that. And then we know the so-called driving frequency of how that works. And then going back to our intro, now that we have the frequency, we have some different data points. We have, let's just say, I didn't actually go into lab yet, so that's why all these are, division by 0. I just wrote a bunch of formulas. So say I can see, 1 node, 2 node, 3 node, all the way up to 5. I measure the period at each of those. So I tune the knob on the engine until I see it as distinctly as I can. And then you go to Logger Pro, find the period, and then 1 over that to get the frequency. And then we go to our trusty viewing an equation as y equals mx plus b, where we have this, 1, 2, 3, 4, 5, 6, 7, however many you can, this via the period, and then we equate this to the slope. And in doing so, you know, solving for v here, we get a value of v, which we can compare to this. You know, this was part 1 should take about 5 seconds. It, in theory, doesn't, I mean, you can measure the length of the string in part 1 if you'd like, as it was stated in the lab manual. But you know, this, you can do it right now. You don't have to do it in lab. And so what we're doing is experimentally, you know, and of course this has a lot of uncertainty based on how, like, if you see the pattern, there's a little bit of wiggle room. You know, there's a range of frequency that you can see the pattern happen. And so your objective here is to compare the two. And let's see, what's next? Next part is that we're going to switch the string. So the string in the first ones was kind of this rubber band type thing. What we're doing in the second part is to change the tension on the string. So getting you know, a normal string in the first part, it was kind of a rubber band string. And in the second part, let's show you what is similarly blocked off. Remember, no measuring the string. We're not going to, you know, all of us touching the same scale for corona times. Measure the length of the string. Should be very similar. Again, mass is given up at the top here. I mean, mass density is given up at the top, depending on what color string you have. Then you are going to pick one of the harmonics, whichever one, you know, looks prettiest to you or you see most distinctly. Similarly, actually, here's another instance of, you know, we've seen it throughout the semester. I would recommend, you know, you can see I copied and pasted it down here, so I'm just gonna delete it because it's annoying. So, you know, those slopes and things like that, you're not, like, you don't, that's not done in a, what's the word, chronological order. You do this first and then you get the slope. So I just moved it down here. So the next thing you do is taking different masses, different tensions on the string. And in doing so, you are going to find different frequencies. Well, first, different periods, getting a frequency, and using this equation here. So the reason we do this, let's show you how this can be done. Starting with this equation, plugging in V from this equation, squaring it to get those things outside, because we want to, our objective here is to take our given mass density and then stretch the string in different tensions to get our own value for the mass density. And so we're going to plug this V into this equation, square both sides of the equation so that we can isolate this mu and solve for mu. And again, doing another of our favorite comparisons to y equals mx plus b, we're going to take this equation, should be written somewhere. Yes, so that after doing what I recommended, plugging that v into the frequency equation, we now have something that can be solved for mu, where in this case, we're changing the mass, so that is the independent quantity. The dependent quantity, which is going to be the y, is the frequency squared. So you have a frequency squared and you have a mass. Again, plot those, get the slope, isolate mu, so you have mu equals something slope. And finally, the uncertainty in this is another one of those it was similar to the oh, what lab was it? It was the one where you had a I believe it was the it was, maybe it was the pendulum lab, where it was the slope was equal to something squared over something, and you have an uncertainty in both of those quantities, and so you need to right, so n constant, 2 constant, g constant, that comes out with the 7. Equation 7 is, you know, the uncertainty of a constant times a quantity that you know. And then you have an L squared, and an, what else? L squared and mu. No, an L squared and an M. Yeah, mu is what you're solving for. So you have an L squared and an M. You have to use equation 9 there because there's two quantities being multiplied together. And then you can use 11 on the L squared. So I hope that made things less daunting for you, because I know that, like, I mean, the reason I made this was because I felt alarmed when I opened this, and it wasn't, you know, pendulums or spinning stuff. So I hope that helps. Let's see, how do I escape, stop share, stop recording.